So the Haas effect is named after this person who wrote this paper in the 50s, I think it was. And he was a guy named Haas, and he was trying to play around with stereo imaging using time as opposed to level. And so we've just sort of shown how that works. So you can actually change the perception of where the sound is coming from by manipulating the delay, or the time that the sound exits the loudspeaker. And if you do that, you can have a very similar effect to actually just changing the level like we did before. However, the advantage of doing it with delay is you get the sense of it coming from a different direction, but it sounds louder because you're hearing the sound twice. Okay, and both of those loudspeakers are actually hitting your ears, and therefore you're perceiving a louder level than you would normally be able to perceive if I had just turned one of them down, and which is what would happen by panning it. Okay, so you get a louder overall perception of the sound, but you still get the sense of it coming from one direction as opposed to the other. Why do you suppose that works? Any ideas? I gave you the hint last week when we talked about acoustics.
Because one is hitting one ear before the other, and they're doubling up because they're within 30 milliseconds of each other?
Yeah, you're close. So, remember I talked about early reflections? So early reflections are these reflections, the sound bounces off of a wall or something, and hits you a little bit later than the direct sound, okay? And if it happens within 30 milliseconds or so, then your brain will sort of interpret that as one single thing as opposed to two different sounds. It will interpret it as one sound that just sounded louder, okay? And that's a critical skill that you've had to develop, because if you couldn't do that, then it's going to be very, very difficult for you to communicate verbally with anybody. Because if you're hearing my voice bouncing off of all kinds of things right now, and if you perceived every one of those reflections as a separate sound, you would have a really difficult time understanding what I was saying. So you've developed this ability to kind of sort out those separate arrivals of the same sound in order to allow you to communicate. It's a critical part of our communication system. So that's why this works. We now, this idea that Hask sort of wrote about has now been kind of really expanded. We use it for lots of different things now. But essentially what was happening when I was panning with delay was I was creating the effect of an early reflection, right? So you had the dry sound would have been the loudspeaker that was not delayed, and then the fake early reflection would be the sound coming out of the loudspeaker that was delayed a little bit. That's just like a sound that came off of a wall that was a little bit farther away, okay? So one of the ways to think about sound systems, if you're designing sound systems, is, if the room had, I hate this word, but good acoustics, because that is a word that's lost a lot of meaning, because a lot of people use that word, but they don't really know what they mean when they say good acoustics. But one of the definitions of good acoustics is that someone can talk in the room. If it was particularly a theater, someone could stand on the stage and talk, and the way that the sound of their voice propagates through the room and bounces off the walls and everything arrives at the audience in a way that it is easy to understand what that person is saying. You haven't lost a whole lot of level. Intelligibility is good. You don't need to really do a whole lot in order to make that voice well heard and understood. That's one definition of good acoustics. And when we design sound systems, a lot of times the reason that we started inventing sound systems was when we started encountering rooms that did not behave acoustically in the way I described. So you have rooms that were designed by the pretty committee and not by somebody who cared about the acoustics. So what ends up happening is now, instead of putting walls up where they should have been, or angling walls the way they should have been angled, we can now instead just hang a loudspeaker everywhere there should have been a wall, basically. So in every place where there was supposed to have been a wall that would have created a good early reflection, you can put a loudspeaker there. And then it sounds like the wall was there, and that loudspeaker is behaving like an early reflection. However, that loudspeaker, the way the sound gets to that is it has to be picked up by a microphone, go through your mixing console, out through an amplifier, and then the loudspeaker. And that doesn't take very long. So you have to delay the loudspeaker a little bit so that the sound is coming out of it at the same time it would have normally come out of it if it was a wall. Because if it was a wall, it would take time for that sound to start from the stage, travel to the wall, and then bounce off. That takes time. Okay? So you got to account for that time it takes to go from the source of the sound to the wall. You add that delay. And one of the most critical walls that we tend to forget to put into new theaters is the ceiling reflector. So if you look at really old theaters that have, quote, good acoustics, they almost always have this really great angled wall, right up over the stage that sort of, angles up. Because then what happens is the sound from the stage goes up to that, and then because of the angle of that reflector, the sound then bounces off of that and points right down to the audience. And it creates a really good, strong first reflection. In the Stevens Center, when they renovated that theater, they put in that big green felt reflector. You've maybe seen that there, that goes up over the stage. That wasn't originally there. They put that there for an acoustic purpose. But then they cut a big hole in the middle of it for a loudspeaker cluster, which means that the place where, usually they put people center stage, and so they're standing right under where the cutout hole is for the loudspeaker cluster, so you don't get that good early reflection that you would normally have gotten with the reflector. So they've created the reflector, but then they just completely compromised it by putting a hole in there for a loudspeaker cluster, because they didn't want to see the sound system. Okay, again, pretty committed. So that's one of the reasons why we tend to really like center clusters for sound reinforcement systems, because a good center cluster that's up over the top of the stage behaves, if you do it right, behaves like a good ceiling reflector. Okay? It does a very similar thing. It has the added benefit of being able to be louder than, the fake reflection that cluster creates can be louder than the natural reflection would have been with a ceiling reflector wall. Okay? And then the same can be said for other things. So anywhere you can also put loudspeakers up under the balcony. Maybe the balcony isn't angled quite well. You can put loudspeakers there where there should have been the angled wall to, again, create a reflection off of the bottom of the balcony. So this is one way of thinking about designing sound systems, but you always have to compensate for the delay time. Because if you want that loudspeaker to behave like it's a wall, you have to delay the sound in such a way that it doesn't come out of the loudspeaker until the time that it would normally have come out if you were trying to do a natural reflection. Okay? So what we do, this is called a precedence effect sound system. And the precedence effect is that essentially says that if you hear two of the same sounds, but one of them comes at you a little bit later than the other one, then you will think that both sounds came from whatever hit you first. Okay? And there's a window of time there that works, and it has to be usually less than 30 milliseconds for like a human voice. But if it's like a drum or something that's very transient, then it might be down closer to 20 or even 15 milliseconds. Much more than that, you'll start hearing an echo. So somewhere in that range is where you want to be. It can be as low as about 5 milliseconds without you being able to notice any dramatic comb filtering. Much less than 5 milliseconds, and you might hear the comb filtering. Sometimes you don't, but sometimes you do. So if you can get those two sounds to arrive at the listener within that 5 to 30 millisecond window from another, then you will think that both sounds came from the first arrival. And if you can make the first arrival be the talker, so the talker's natural voice hits the audience before any sound comes out of the loudspeaker, then when the sound comes out of the loudspeaker and hits the audience a little bit later, they will think that the sound that came out of the loudspeaker actually came out of the person who's standing there on the stage talking. It's a very cool trick. There's two other rules of thumb for this. So the first one was 5 to 30 milliseconds apart. The second rule is no more than 10 dB difference in level between them. Okay, so you can take that reflected sound or that delayed sound, it can be as much as 10 dB louder and still image. But if you go much more than 10 dB louder, then you will start to perceive the sound as coming from the delayed source as opposed to the original, because the level, the level difference overrides the time difference essentially. Okay, so can't do much more than 10 dB. The third rule is that the sound coming out of that loudspeaker needs to sound just like the thing that came out of the talker. Okay, if what comes out of the loudspeaker is different, vastly different, then your brain will not put them together. Your brain will assume they are two different sounds. So this is why you have to spend a lot of time really EQing and tuning those microphones so that the sound that comes out of that loudspeaker of that person's voice sounds very, very similar, as close as you can possibly get to what came out of their naturally. Okay, so if you can get all three of those things to happen, then you get to make the show louder, which is nice, right? You get some gain. The audience thinks that the show is louder, but they think all that sound came from the talker. It just sounds like the person's talking louder, when in reality they aren't. And no one knows you did it. So you get none of the recognition and none of the credit, but you get paid well. Yeah?
Is precedence something that's always worried about? Because like a rock concert, they just when it's so loud that it doesn't matter. But like for theater, is that something every single time you're trying to do?
Not always. Certainly there might be things that are more important to you in shows. If it's like a rock musical or something, maybe you don't care so much. But I usually, even with a really loud show, I will usually try to build in the ability to have a precedence image, if nothing else for the dialogue moments, because I really want my shows to have a dynamic range. I don't want them to be full on loud for the entire 2.5 hours. I'd like to be able to have that dynamic range, wax and wane, as we go through the show. That makes it more interesting to listen to. It makes the loud moments more powerful if they sound vastly different from the quiet moments. So yeah, I have seen actually a lot of people make a mistake where they spend a whole lot of time trying to create a precedence system when, at the expense of something that is probably more important for this particular show. So this is not necessarily the solution for every project you do, but it is a solution that I would say the vast majority of the time for musical theater it is a desirable effect, something that is worth doing and that people will be happy about achieving. So that's what we're going to do today, is talk about how we can make that work. And then I'm going to give you a project where you're going to do it. So let me show you first. We're going to go through, let's see. We're going to try it in the Stevens Center. Let's do that one. So this is not a difficult thing to figure out, but it does involve keeping track of a lot of information. And unfortunately, there aren't very many. This is one of the few things out there that no one has yet really been able to develop a very effective computer program to do this for you. So you kind of have to do this yourself. I have tried before to create a computer program that would do it. I've had limited success in that, but it is possible. All right, so ultimately, you know that we have these two components of our sound system, right? 4 components, really. So you've got a loudspeaker, a microphone, a talker, and a listener. You remember that? So we're going to put all of those things into my sound system here. And just to make the math easier, I'm going to go ahead and scale this. Oh, let's see. Okay, so I'm gonna pretend like I'm gonna bring in my own center cluster for this show. So I'm gonna hang it underneath the eyebrow here, and change my point style here again. There we go. Okay, so I'm going to put my center cluster there, and where should we put our talker? Maybe somewhere right there, 5 feet up. Let's say this is graduation. Okay, we're going to have a podium, downstage center, okay, or something. But yeah, somewhere that doesn't really matter. We can put them anywhere we want. I also want to find out. You have to solve this problem from the point of view of the audience. Okay. The answer to this problem is how much delay do I need to put on the center cluster? That's the answer we're looking for. But we figure that out by solving it from the point of view of the listener, because it's the listener that hears the precedence effect. Okay. That's another mistake I see people make. Is the answer is about the center cluster, but the problem is about the listener. So you got to remember to look at the listener here. So I'm going to put a point here for a listener at the front row. I'll put a point here for the listener at the back row. And let's do the balcony as well. So I'll put a point here for the front row balcony. And I'll put one for the back row balcony. Something like that, okay? And then just to help make sense of everything, I'm going to go ahead and label these seats. So that'll be seat A. That'll be seat B. Seat C. And seat D. Okay? And I find it much easier to do this if I use a spreadsheet to help me keep track of everything. So I'm going to pull up Excel here, which you all should have free access to. And I'm going to solve this for each seat, okay? So what I want to find out is, I'm going to call this seat A, seat B, C, and D. And I'll have talker distance. So this will be the distance of the talker to each of these seats. It's the first thing I want to find out, okay? Because ultimately I'm trying to figure out how much delay I need to put on the center cluster to make sure the center cluster hits the listeners after the talker. So the first thing I need to find out is how far away is the talker. So the talker is, let's see, talker is 26.24 feet from seat A.
Isn't hand zoom a little bit?
Yeah. Let's see here. Yay. Okay, let's do now distance from the talker to the back row, which is seat B. 82.42 feet. Okay. Now we'll do talker to seat C, 63.34 feet. Okay. And we'll do this again to seat D, 105.34. Okay, so that's how far away the talker is from each of those seats. But I want to know how long it will take for the sound from that talker to reach those seats. And distance is not the same value as time. Okay? So what would I have to do to convert this distance into time?
divide it, or divide our 1130 divided by.
So yeah, if sound travels 1,130 feet per second, then that means it will travel 1.13 feet per millisecond. Okay, so remember that 1.13 is that magic number that we can use. We either multiply or divide by 1.13, and we can convert from between distance and time. So because distance is usually longer than time when sound, we're going to divide the distance by 1.13, and we will get time, because time is less, okay, usually. So you can actually get Excel to do this math for you. Do you guys know how to do formulas in Excel?
Yep.
You guys aren't learning these things like in high school or anything?
I took a computer class in 6th grade.
All right, so here's what I'm going to do. I'm going to use a formula to calculate this for me. So to type a formula, you just type equals. And then I'm going to click on this cell. So say whatever value is in that cell divided by 1.13. Okay? And I get that number. And then watch this little trick. If I just kind of take this little handle and drag it across, it will migrate that formula, and it will change the variable definition for the cell. See that? It goes from B2, C2, D2, E2. All right? So that's time. That's how long it will take for the sound to get to those listeners.
That's in milliseconds?
That's in milliseconds. All right, so the next thing I want to find out is how far away is the center cluster from each of these seats. So center cluster to seat A is 33 feet, 33.01. So this is center cluster distance. Okay? Let me save this while I'm thinking about it. And now let's try to seat B, 76.80. Let's try it to seat C, 50.66. And to seat D is 89.79. Okay, that's distance. Now if I want time, I can just, again, do equals that divided by 1.13. It is a smaller number, so I think it's probably right, and I'll just copy those over. Now I've got it. So now what I want to find out, now I've got the times that it takes for the talker to get to all 4 seats and the time it takes for the center cluster to get to all 4 seats. The presumption is if I can make this work for all those 4 seats, it probably will work for all the seats in between. Right? If it works at the front row and it works at the back row, it probably works everywhere between the front row and the back row. Very rare situations where it wouldn't, but almost always that works. Okay? So I'm doing front row for both orchestra and balcony. If I can make those work, it'll work everywhere else. So what I want to find out is now what is the difference in time between these two things? Right?
Yes.
So I'm going to say, well, let me ask you this. Which one do I want to have arrive first?
Talker.
The talker, right? So if this was working, the center cluster would take more time to get to the listener than the talker would.
Yep.
Okay? So I'm going to do a formula here, which is center cluster minus talker. Okay? And if the center cluster is arriving after the talker, then I should get a positive number from this equation, right? And if that is a positive number, that is more than 5 milliseconds but less than 30, then I know that the imaging will work. Okay? So let's try it. I'm going to say equals the center cluster time minus the talker time. And I get almost 6 milliseconds. Okay, so it works at the front row. I don't have to do anything. It already works. So if I copy this over now, let's see what happens. Okay, all these other ones are negative numbers, which means in all of those other situations, the center cluster is arriving first. So for seat B, the center cluster is arriving 5 milliseconds before the talker. For seat C, the center cluster is arriving 11 milliseconds before the talker. And for seat D, the center cluster is arriving 13 milliseconds before the talker. Okay? Great. So that's not exactly what I want, though. I would like all of those things to be positive numbers between 5 and 30 milliseconds, right? So how could I make that happen?
Delay?
Yeah, I could add delay. So let me add a field over here for center cluster delay. So how much delay would I need to add to the center cluster to turn all of these numbers into positive numbers that are at least 5?
Like 19 milliseconds.
Yeah. Let's make it an even 20. So I'm going to say 20 milliseconds. And now let's see what happens. So I'm going to modify my formula to say I want B5 plus center cluster delay minus the talker. Okay? There that works. Okay? And now this is just a little trick. Watch what happens if I copy these over like this. It won't quite work because see how it migrates the H over to an I and then to a J. So that doesn't track. So let me show you how to keep that from happening. If you put a $sign in front of both of those, the H and the 2, then that tells it not to move that cell when you copy the formula. Okay? Just a little trick. All right, so it's working. That would work.
Why would you add delay to the seat that's already in the black? The seat that.
Well, I'm adding delay to the center cluster. So if I add the delay to the center cluster, then that changes the time the sound comes out of it. So it affects all the rows.
Yeah, of course. All right. I
So
just missed it.
yes, that would be awesome if I could change the time for
That
some of them,
guy.
but not the other ones, right? That'd be great. But I don't usually have that luxury. So here's what's interesting about this. It's kind of right on the edge of working. That the sweet spot here is 10 milliseconds. Remember I said that it can be as much as 10 dB difference between the two? Well, the situation where you can have that center cluster hitting the audience 10 dB louder is when there is a 10 millisecond difference. As you drift away from that 10 millisecond difference, you stop being able to get that full 10 dB of extra gain before the imaging starts breaking. So the closest one is seat D to that. And I can't, if I play around with this, I'll never get all 4 seats to be that perfect 10. Because right now, the center cluster is rapidly approaching an echo at the front row. But I'm only 8 milliseconds at the back row balcony. So to get the back row to be at the 10 milliseconds, the front row has to be just barely short of echo. See that? So, but we can make it work. Yes?
Can it not be 10 seconds of low to make it work?
No. If you go less, then it's an equilibrium thing. So the further away you get from 10 milliseconds, the farther away you get from being able to get that perfect 10 dB increase.
So it needs to be 10 milliseconds with 10 dB increase.
Yeah. Sorry. Put that there. Hang on. Let me go grab a towel.